Hello everyone. I thought I would make a quick tutorial for you on how to run a t-test so that you can complete your lab write-ups in case you had some questions on what a t-test does, how it works, and what you need to do to use the results from a t-test. So this summer you had some summer homework where you used a chi-squared table, and a t-test table is very similar to a chi-squared table. However, a chi-squared value is looking at expected as compared to obtained values. T-tests are looking at two different sets of data that you can compare the means on. You looked at something similar to this table where you had degrees of freedom going down one side and you had p-values up at the top, and you calculated a value and then you had to find whether or not it was significant at a certain p-value. And what that significance means is whether or not it is likely that the results that you obtained were due to random chance or they were due to the manipulation that occurred on the independent variable. On this particular table, there is it's combined between a one-tailed set of data and a two-tailed. And what that means is on a one-tailed data table up here, there's these two pictures. And one-tailed says we only care about if there is data, a difference on looking at one side. And two-tailed is saying, well, we don't really care which side of this distribution the difference occurs on. We just want to know, is there a difference? So in a really oversimplified way, that's the difference between a one-tailed and a two-tailed test. So you guys are going to be most often looking at two-tailed tests right here. So we're going to use this row right here when we're looking at p-values. So let's do a quick review on p-values. So remember that the the accepted norm for when something is statistically significant is when its p-value is at 0.05. So if you take that and you translate that into a percentage, this says that at a 5%, so 0.05, if you took that and put that in a percentage, so that's saying there's a 5% probability that the results that you obtained were due to random events or random chance, and a 95% probability or certainty that they were due to the manipulation of your independent variable. If you move down this direction, now it's even higher. So it's a 2% probability that they were due to random chance and a 98% probability that they were due to whatever you manipulated for your independent variable. Move down this direction and now you're at a 1% chance of random probability and 99% chance that they were due to manipulation of your independent variable. But what happens if we move up from 0.05? If we go up here at 0.1, we're now at a 10% probability that random chance caused your results, and 90% probability that it was due to your independent variability or independent variable manipulation. Now you're at 20% chance of random events causing your results, and 80% certainty that it was due to whatever you changed. And as you move closer and closer to 1, you become less and less certain that whatever your results are were due to whatever you manipulated. And as you move closer and closer to 0, going the other direction, you become more certain that it was due to the things that you changed. So originally, when you guys were using tables during the summer, you came down here, you looked at the degrees of freedom, you looked at a value that you obtained, and then you figured out where that value fell within this table. I'm going to show you a shorter way to do this. We're going to calculate your p-values directly using Excel. However, because this is recording using an online format, we're actually going to use Google Spreadsheets, but it works the same way as Excel. So I have set up a kind of a fake spreadsheet situation in here, and I've got my 3 trials for control and 3 trials for experimental, and I'm going to put in some fake data. So I'm going to say that I did the pectinase lab, and I recorded some values for my control group, and let's say that I got 17 milliliters. I don't want to put data in that one, I want to put it up here. Sorry, I'm going to clear this data cell. So I got 17 milliliters of juice, and I got 14 milliliters of juice, and I got 16 milliliters of juice. And then for my experimental group, let's say I got 23 and 20 and 19. So looking at those numbers, if I took the averages of that, I would find that those averages are different from each other. And it would appear at first glance that they would be significantly different, because the average of this is going to be about 15 and a half. And the average of that is going to be about 21 or so, without calculating them. But so that they'll be different from each other. But I don't know if that difference actually matters. And that's the question that a t-test will answer for me. So I need to know, does the difference between the two means matter? And at what level does it matter? Am I likely to be able to say with 95% certainty or more or less that the difference was likely due to the change in my independent variable? So can I reject my null, or do I need to fail to reject my null? So the way to do this is to run a t-test. And again, I'm choosing a t-test because I'm looking at two sets of data. I'm not looking at an observed as compared to an expected value, which is what you would do with the chi-squared test. So on my spreadsheet, I could put my value here, I could put it over here, I could put my test here. I can put it anywhere on my spreadsheet, it doesn't really matter, but I'm just going to choose to put it here. And I can type my formula up there, or I can type it into the box. But I'm going to type equals t.test, that's the command for a t-test. And if I click on it, it will pull up what I need to put in here. Now if you're putting this into Excel instead of Google Sheets, instead of saying range 1 and range 2, in Excel it says array 1 and array 2, but it's saying the same thing. It's just asking you, what is your first data set and what is your second data set? So this first one is in column B, and it's rows 2, 3, and 4. And I can select that and just pull it down like that, and it will enter it in. Or, and then you separate it by a comma, or I can enter it because I know what it's going to be. So my second one happened to be C2 to C4, because that was what my next column over. When I'm looking at the type of tails, again, if you remember back to that graph, the picture of the graph, I wanted to know, is there a change? I don't care if it's on one side, or like just on the positive side or just on the negative side. I want to know, is there a change? So I'm going to select a two-tailed test, which is what you guys are going to pick. So you're going to put 2 in there. On the type of the test, there's different types of t-tests that you can run. Type 1 is a paired test. So this would be something where, for example, if you were testing a person so that they were their own control. So maybe you gave a person a pre-test and you gave that same person a post-test. They were paired with themselves. So you would use a type 1. In our case, we're going to use a type 2. So you're going to put a 2 in there and close parentheses. So now we have our formula in here to run our t-test. And then you're going to hit enter. And it's going to calculate a p-value for you. So now I have my p-value directly calculated. My p-value is 0.28. Looking at this number, my question is, so what does this number mean? What does this tell me? First thing I want to ask myself is this greater than or less than 0.05? because again, that's my level of statistical significance. That's the point from a scientific point of view where I get to determine whether or not I'm going to fail to reject or reject my null hypothesis. So this is less than 0.05. So what does that mean? That means that I am going to reject my null hypothesis. So this says that there is a 2.8 roughly % chance that my results were due to random error, and an about 97% chance, or 98.2% chance that it was due, 97.2% chance that it was due to whatever I manipulated in my independent variable. So that's pretty good. That's pretty certain, which means that I will reject my null hypothesis. But let's change around this data a little bit. Let's say that instead of my control having this, maybe my control was 18, and now, even though these appeared to be different at first glance, look what happened down here on my p-value. I'm now at 0.51. And I'm like, that's so close to 0.5, but guess what? It's still over 0.5, which means I am now no longer 95% certain that my results were obtained due to the manipulation of my independent variable. So in this case, I failed to reject my null hypothesis. And most of the time, it's not going to be quite that close. In this circumstance, that's what it is. And remember, one thing about science is that science is not about wrong or right. So just because I'm going to reject or fail to reject my null hypothesis in this circumstance doesn't make my experiment wrong. It just is what it is. That's what the data shows. So in this circumstance, I would say that because my p-value indicates a number of 0.51, which is greater than 0.05, I fail to reject my null hypothesis. This indicates that there's a greater than 5% probability that the results were due to random chance or random error, and less than 95% certainty that the results were due to manipulating the independent variable, even though it's so close. But that's a great point for discussion. Maybe this would be improved with more trials. Maybe there were other sources of error that could be controlled for to see what would happen, which is always why more trials are always better. So that's how t-testing works. Your goal on running that t-test is to get that p-value right there. You want to know, what is the p-value, which is going to answer the question, is the difference between the average of this data set and the average of that data set meaningful? And at what level is it meaningful? So this difference is meaningful as long as it is above a 95% certainty level. So if I am not worried about being 95% certain, then it's meaningful. But if I need to be 95% certain, then that difference is not meaningful. And that's what the t-test will answer for you. So I hope that will help you as you go through and work on your statistical analysis of your data for your lab. But that's an easy way to be able to complete the t-test. It's just to enter in this formula. It will work the same way in your Excel spreadsheet that it does in Google Sheets. The only difference is that in Excel, instead of being called a range, these numbers are called an array, but you still enter them the same way. It's just the column of the data for each thing. You'll still run a two-tailed test, and it will be a type 2. So that's it. Enjoy. Good luck.